Okay, so lecture 5. So today and on Thursday we will be well, technically introducing, but given the speed we are going at, reviewing some of the basic material about differential geometry. I'm saying reviewing because we will be going quite fast, but I'm not supposing you know anything about it. Obviously, if you really don't know anything about differential geometry, understanding everything we say will be a bit difficult. So try and grasp the general idea, and then you can work out the details later. Okay, so the first point is abstract manifolds. What I mean by abstract manifolds. For now, we've been dealing with submanifolds of Rn. So our objects were subsets of Rn with some additional properties, like being locally a graph, being locally the zero of a matrix of a function with the Jacobian matrix of full rank, or being locally parameterized by an open set, a ball of Rk. Now, not everything comes naturally, or at least easily, as a submanifold over N. For example, say you have a problem and some geometric problem, you have to find some line in R3. So some line through the origin of R3. The set of all lines through the origin of R3, I mean, you could think it's a sphere, but it's not, because it's a sphere where opposite points are the same, because they are the same line. Now, this kind of construction is called quotient. So you have some relation between the points, maybe in terms of geometric transformations or some other kind of transformation that tells you that 2 points should be actually the same. And you want to consider only the equivalence classes. So, for example, you have the sphere, and you want to consider opposite points as being the same point. If you try and glue up these points, you cannot do it in R3. So you start from a sphere, but you cannot do it in R3. Now, you can realize this weird space, which is called projective plane, in some Rn, but it's not natural. I mean, that depends on your definition of natural. It's not intuitive, let's say. And or, for example, you want to consider not really orthogonal matrices, which are a nice submanifold of R9, but you want to consider orthonormal basis, or which would be the same, or maybe orthonormal basis up to change of coordinates, because you're only interested on the 3 directions, and not which is the first, which is the second, which is the third. And this is a quotient of the orthogonal group, or stuff like that. I mean, you can always, at some point, find an Rn, which n may be bigger than the starting one. For example, the orthogonal group is in R9. Maybe you have to go to R something else to find an embedding of, to realize this set as an embedded submanifold over N. But sometimes it's not intuitive, it's not then easy to work with such an embedding. So we would like to have a notion of manifold without having to be into Rn. These are some of the reasons. Now, this definition, something which is locally like Rn, makes sense in Rn. or local RK makes sense in Rn because we know what a smooth map is. So we can say that they are diffeomorphic because we are saying that there is a map from a neighborhood of our manifold to Rk, which is on our manifold diffeomorphism. Okay. Now we take a generic set. So a set, some set of points, not even in Rn. A coordinate chart for M is a pair set function where the set is a subset of M and the function is a bijection, so a one-to-one correspondence between the set in M and some open set in Rk. Okay, this is a chart. It's called a coordinate chart because the function phi gives you coordinates on your points. So what does that mean? You have some open set U you have a function phi into some let's say ball V in Rk. So on here you have coordinates. So, well, for example, here it's R2, so you have X is now the inside of your set goes inside your ball. In any way, this is just a function, okay? Now, if you take a point here, you can follow it and it goes to some point here. For this point, you have coordinates. So the coordinates of Rk. So if this is P inside M, this is phi 1 of P, and this is phi 2 of P. So for each point of your set U, you have, in this case 2, but in general K coordinates. So this is why this is called, and these are unique, and every pair, every K tuple of coordinates determines one point in U. So this is why U phi is called a coordinate chart. Now, you can do that in a lot of ways. So this doesn't mean anything for now. Now, if you take two charts, so you have two sets on your M and two functions to Rk, they are compatible if either they are disjoint, so that the two sets on M don't intersect, so okay, or they are not disjoint and two things happen. First, well, they're not disjoints, it means there is an intersection between the two sets. Now, this intersection must go through both the functions to open sets in Rk. So this will be an open set in V1, and this will be an open set in V2. And this weird condition. So now, what does that mean? You have M you have the two sets any of the two functions. You end up with two open sets, let's say V1 and V2 in Rk. Now, first thing first, you have this intersection. If you look just at the map phi1, the first hypothesis tells you that this goes in an open set here, a subset of V1 which is still open, and it goes in another open set here. Now you can go from here to here in this way. From here you go up, with the inverse of phi1. Remember, phi1 is a bijection, so you can invert it. So from this open set in Rk, you go up here, and this is phi1 technically restricted to this open set. And then you go down here. I mean, this is phi2, even if technically is phi2 restricted to just the intersection. So if you follow the two arrows, you end up with this function here, which is the composition of the two. So is first doing phi1 to the -1, so the inverse, and then composing it with phi2. Now, this red map is from an open set of Rk to an open set of Rk. So for this red map, we can ask that it is anything like smooth, a diffeomorphism, whatever, because it's in Rk. So if we are asking it to be smooth, we just mean that the k components of the map are differentiable functions of the k coordinates. And to ask that it's a diffeomorphism just means that the Jacobian matrix has to be an invertible matrix. And this has to be injective. By the way, this function is injective because it's a composition of injective maps. And I mean, phi1 and phi2 are bijections, so the set theoretic part works. The only thing we have to worry about is that we ask that this has to be a diffeomorphism. So technically this is restricted again to the intersection, the image of the intersection. By the way, here is a U. Anyway. Okay, so this is the delicate point. Is this clear? If there are any questions at this point, ask me. So these are two charts. So these are two sets in M with some bijections on open sets of Rk. So I identify them with two open sets in Rk. The whole point is that they are compatible if when they overlap, I can change from one coordinate chart to the other coordinate chart with a diffeomorphism. So the relation between the points here and the points here, the way they glue, it's smooth. Okay? So if you want to see it another way, we are describing our M as pieces of Rk glued together in a smooth way. So this this function here, this function here, you can call it, it's a change of coordinates, or sometimes gluing function. So because it tells you how the open set should glue up. So with the same open sets, you can glue them up in different ways and obtain different spaces. Okay. So this is an upstart manifold. Well, no, this is compatible charts. Now, a smooth structure, an atlas for M is a collection of compatible charts such that the union of the sets cover the whole M. Two atlases are compatible if once you join them you get again an atlas, so if all the charts in every possible combination are compatible. And a smooth structure, or a manifold structure, is a maximal atlas, is an atlas as big as it can be. So you cannot add any more charts. Anyway, this is all the whole theoretical setting. The whole point is that you've covered up your set with pieces of RK that overlap and that glue in a smooth way. So you've given coordinates in every part, and when you change the map you're using, the chart you're using, the coordinates change smoothly, okay? So a smooth k-dimensional manifold is a set M endowed with a smooth structure whose charts take values in RK. So it's taking pieces of RK and gluing them up together in a smooth way. Okay. Okay, but anyway. Now, what is a smooth map? Now everything is easy in a way, because what is a smooth map? Is a function from two manifolds which is smooth in every chart. So again, we have here our M, and we have another kind of, so the drawings are the same, because I mean you cannot draw in too many dimensions, but here is our N. I mean, these are both surfaces, but whatever, I mean 3, 4, I mean any dimension, and they don't have to be the same dimension. And you have a function, f. What does it mean that the function is smooth? Well, it means, I mean, on M and on N, you have coordinate charts. So however you take a coordinate chart here and a coordinate chart there, so if you take some coordinate chart here, and some coordinate chart there, obviously this goes to an open set in RK, and this goes to some other open set in RH. Now, let's say this is f of u, So we take the image of f of u, and we suppose that f of u intersects our v. So down here we have some part of our intersection. Now, we can restrict only to the part, I mean, we can make it such that f of u is contained in f of v. But anyway, so we will have, well, we can look at the pre-image of the intersection, we get another intersection, so in the end, we get that the pink, purple, whatever set goes to the orange inside of U, goes to the orange set inside of V. Now, what can we do? We can, as before, define a function here, which is going up with the inverse of phi, going through f, and then going down with psi. So we have psi composed with f, composed with phi to the minus 1, which in general will be defined on a small part. We ask this map to be smooth. Okay? So the requiring is that this map is smooth. So smooth maps are between manifolds are just things that when you go down via the coordinate charts are smooth between sets of Rk and Rh, open sets. So it just means that the components are C infinity or whatever. Now, the technical points, I don't care too much about that. On Rn, there are infinitely many smooth structures, and you can try and find how many. All these structures are diffeomorphic if n isn't 4. So if you take two smooth structures on R3, for example, you have a diffeomorphism between them. So you have a map which is smooth from R3 to R3 with two different smooth structures, and that is invertible. You know what diffeomorphism is. This is a bit tricky, however. It's a game on the definition. For n equal 4, there are smooth structures on R4 that are not diffeomorphic. So R4 is a very, very wild beast. And if you are interested in that, giving a smooth structures means also giving a topology. We won't be entering in that, but we can talk about open sets on M. So it means things that are open once we look down via a coordinate chart. Okay, I hope this is clear because it's the foundation of everything. We won't be needing the technical details of this. I mean, if you want to study differential geometry in depth, obviously you need them, but we won't be needing them to the proof level. We will just be needing the idea. So you should be comfortable a bit with the idea of manifold and of smooth structure. Then everything works like in the submanifolds of Rn, but I mean. Now, tangent vectors. This is the other not so easy part. We need to say what a tangent vector is. Okay, so tangent vectors on a manifolds were sort of way to differentiate functions along a direction on the manifold. So if you remember, that was our starting point. We said, okay, what does it mean to differentiate something along the manifold? We take a curve inside the manifold that goes through our point, and we compose f with the curve, and we take the derivative at the point. That being said, we defined the tangent space to a submanifold of Rn as the set of all directions a curve can have if the curve lies on the manifold. Now this gives a way to differentiate functions. Here we cannot anymore talk about the speed of the curve because we don't have any intrinsic way to define the speed, so we are looking for that. But we have a way to define derivatives. Now, we have a smooth manifold, we have a point. Okay, C infinity of M is, well, okay, the ring of smooth maps. Why did I write that? Is the smooth functions from M to R. So we define what smooth maps between two manifolds are. If the target manifold is the real line with the usual smooth structure, you could say, then a smooth map is, in that sense, is just a C infinity function from your manifold to R. It's a ring because you have sum and product, but who cares? A tangent vector is a linear functional x sub p on C infinity of M, so is something that takes every function and gives you a real number for each function in a linear way. So if you have the sum of two functions, the result is the sum of the results, and if you multiply by a scalar, the function, you get again the scalar times the result. And this holds. I hope you recognize this. Take like 30 seconds, look at it, and tell me in the chat or whatever that you recognize it. So instead of x sub p, think it about, x sub p should be a derivative. So what is this? The derivative at p. Exactly, it's the Leibniz rule. So the derivative of a product is one function times the derivative of the other plus the other thing. Now, unsurprisingly, it's such a functional, so something which takes a function and gives you a number and it's related to a point p is called a derivation at p. It's not a derivative because it's the derivation, but it's the same thing, okay? This is an abstract algebraic way to define derivatives. So we are saying the tangent space is all the ways we can take a derivative at p. This is a vector space because these are all the linear maps from a vector space to another, so it's a vector space. And we denote it by TPM, the vector space of all tangent vectors to M at P. Now, to understand a bit, or maybe to deepen your confusion, what happens in a chart? So we take a chart. We take a chart around P, such that P goes to the origin of Rk. And we take a function, the C infinity function on the manifold. By definition, if you remember 2 slides before, being C infinity from the manifold to R, it means that once you go, you look at things on a coordinate chart, in coordinates, you get a usual C infinity function from your open set in Rk to R. So if we take this composition, nope. Okay, this is not C infinity of M, it's C infinity of Rk. So here you should have Rk. Well, anyway, it's not important. I will correct it later. Now, so if you take a function on Rk, if you compose it with phi, you get a function on M, and this is again C infinity because of the definition. Now we define phi star of xp as applying xp to u compose phi. If you do the calculations, this is a derivation, so it has the same property before. It's linear and it obeys Leibniz rule on functions of Rk. So this u is a function of Rk, and we build a derivation by this formula. We apply xp, a tangent vector, to m, to the composition of u with phi. So we have m, and we have u. We have our coordinate chart to u to v in Rk. Now we take a smooth map to a real line. We can again compose here and get a smooth map from u to the real line. Now you can just set it to 0 outside some compact set, and you have a function on m. And we can apply our xp, which is a derivation at p here. So we have our p here, which goes to the origin. We apply our derivation here to this function. So we get some linear functional on smooth maps in Rk. It's a derivation, but derivations in Rk are tangent vectors, which are directional derivatives. A derivation in Rk is just a directional derivative, so it's du in dv for some vector v, but it means is v1 times the directional derivative. V1 is a number. Directional derivative in the first variable, partial derivative in the first variable, plus vk partial derivative in the kth variable, evaluated in 0. Okay, this fact should be proved that all the derivations on Rk are of this form, but this is quite easy. This fact I hope you all know. I mean, a directional derivative is just a combination of the partial derivatives. Now, on Rk, you have global vector fields given by the k partial derivatives. So the partial derivative in x1 is a vector field on Rk, because for each point of Rk gives you a way to derive the function, differentiate the function, actually. And so it corresponds to a tangent vector. So also in the sense we gave in the previous lectures. So the d in dx1 is a tangent vector in Rk in every way you look at it, also in the submanifold way we talked about before. It corresponds to the curve going in the x1 direction. Gamma of t equals t times e1. If you want to take the partial derivative in the second variable, you have gamma of t equal t times e2, etc. Now, these k partial derivatives give you a basis of the tangent space at every point of Rk. That's why they are called a global frame. Now, in differential geometry, many names have been given, or at least have been also used by physicists, so you have a lot of weird words like frame. But they're global basis, but they're a global frame of reference for the tangent space. So meaning you have vector fields such that at every point they give you a basis of the tangent space. So that means that you can actually write down your tangent space in terms of them at each point. It is easy to check that phi star gives you an isomorphism between the tangent space at P and Rk. because phi was a bijection between your space and Rk. Now, the tangent bundle. We can glue up all the tangent spaces. So we build the set of couples, points, tangent vector. The point is on M, and the tangent vector is in the tangent space of P, like we did in Rk. Now, we should prove that this is again a manifold. How? Well, the charts are sets of the form U times Rk, and the map is phi star, and phi star is the one from the previous slide. Now you just have to check that everything goes smoothly, and that different charts are compatible and whatever. And the projection is a smooth map. Like in the submanifold case, a tangent vector field is a smooth section. So it's a smooth map from M to the tangent bundle of M, such that at each point the image lies in the tangent space at P. So it's a selection for each point of a tangent vector. Like in the submanifold case, if you have a smooth map, you have a map between tangent spaces, defined like this. So your tangent vector xp, tangent to M at point P, is a functional of smooth maps. So to define its image, we have to take a smooth map on N, the target, and tell what how the image acts on F. So here there should be an F. It's just F star XP of F, which is XP composed of subscript star F. I mean, the definition is the same we gave for phi star. Is XP calculated on F composed F. So, okay, they both called F. Small f goes to N from N to R. If you compose it with big F, you get something which goes from M to N and then from N to R. So you end up with a function here that goes from M to R. So this composition is a smooth function from M to R. Now we apply to it your tangent vector, which is a way to differentiate the function, and you get a result for each function on N. And this gives you a derivation on N. So a tangent vector field to some point f of p in N. The resulting map between tangent bundles is also denoted by f subscript star. Now, usually people say just say f star, but we will be having f subscript star and f subscript star. So also subscript and subscript are not really easy. But anyway, they have a name, but, well, this is called push forward, because it takes something on M and pushes it forward to N. So it takes a tangent vector to the origin and pushes it forward to a tangent vector on the target. But sometimes it's just called differential of f. Now, let's see why. Okay, first the notation, we denote by this symbol, Gothic X of M, or by gamma MTM, the set of vector fields. Gamma MTM technically means the sections, gamma, on M of Tm. So the functions from M to Tm such that blah, 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 smooth sections. Okay, if you have a chart, we denote by x1, xk the components of phi. So technically, x1, xk are functions on Rk, usually. So we maybe should be writing phi 1, phi k, but I mean, to keep the notation decent, we just write x1, xk. So like what I said in the beginning, if you have your phi, you can associate to a point the coordinates. So let's say that these coordinates are the maps x1, xk. So we won't be considering phi anymore, because if we change phi, the coordinates change in a very nice way, smooth way. So we don't care, we just take the coordinates. These coordinates are not global, they don't exist all over M, they just exist in U. Now, we consider vector fields, which we denote weirdly by partial 1, partial k, such that partial j xi is equal to delta ji. Okay, just a quick note. I think you all know, but this is just 0 if they are different, and 1 if they require the delta function. So these vector fields at any point are defined by this relation. Now you can easily check that if you push forward any of these vector fields to Rk, so if you do phi star like we did in the beginning 3 slides ago, and you apply it to any function on Rk, you get just the jth partial derivative of f. So in some sense, these are the vector fields on your manifold that corresponds via your coordinate chart to the partial derivatives on Rk. Now, on Rk, they are a global definition. On your manifold, they live only in your open set where you have your coordinate chart. Now, every vector field in your U, in your open set U, can be written as x1p plus xkp times these vector fields, these basis vector fields. Or compactly, this is a notation you will find a lot of times in differential geometry, xj times partial j, so dj. What does it mean? I mean, the index is repeated jj, so it's understood that we are summing on that index. So anytime you see a repeated index, it means we understand a summation on that index. This is called Einstein notation. I'm sorry for that, but it's a thing. So, by the way, usually you sum indexes that are opposed. One is up and one is down. And being up or down has a meaning, but one step at a time. Now, D1, dk give a basis of TPM for P in U. They are called the local frame. Every time you have a coordinate chart, you have a local frame. So you can actually forget about the basis, which is some sort of canonical on U, on U phi, and just talk about the coordinates. Now, once you have a local frame, you can perform local computations, meaning that you end up with functions like those xj. These x1, xk are functions from your U to R that give you the coordinates with respect to this basis. So you can perform local computations because you just have coordinates x1, xk like in Rn, and you have function of those coordinates, and you can take partial derivatives and whatever. If you do things right, if you deal with the right quantities, you end up something which is independent from the local frame, so it's independent of the chart you are taking. It means that it has to be a property which is sort of like the compatibility of charts. Now, in many times when you use a vector field, so A, Aj, Dj, you just write down its components, so A1, Ak. Now, what does it mean to apply the vector field to a function? It means to take Aj times the partial derivative of f with respect to a coordinate j. So again, this partial derivative is the partial derivative once you go down via a coordinate chart, is the application of that vector field on f when you are on the manifold. But again, if you write down f with respect to the local coordinates, this is just the partial derivative. Some more confusing notation. The index for coordinates of vector fields is a superscript. The index for vector fields is a subscript. This is an old notation, so I don't think you will find it, but sometimes writing comma h or semicolon h, or this one, which is the usual one, denotes the partial derivative of the function with respect to the local coordinate. This is not invariant with respect to the change of coordinates, because once you change the coordinates, the first coordinate of the first chart becomes something in the second chart. It's not even a coordinate, maybe. It's just a function. Now, push forward in coordinates. So if you take f and the vector field on M, you push it forward, you apply the differential of f, and you get y equals f star of x. And you know that this relation holds. So if you apply y to any function, you are applying x to the composition. Now you can take local coordinates on M, local coordinates on N, and you have local frames, the xi and the yj. I'm using x and y to distinguish the two local frames. So, by definition, you have these. Y is a function of the coordinates. Sorry, no. Okay. So the coordinates of the vector field are just the vector field applied to the coordinate functions. So you can write y as y applied to the coordinate times the partial derivative, which is, by definition, x applied to the coordinate composed with big F times the local basis, which is, by definition, x, the component of x, times the derivative with respect to x of y. So you are, ignore everything else. Focus on this part here. Or here, with also f. Now you are taking the derivative with respect to the x coordinates of the y coordinates. And you have a relation between the y's and the x's given by f. So y equals f of x. You are differentiating the new coordinates with respect to the old coordinates. This is just the Jacobian matrix of f written in local coordinates. Or better, if you remember the drawing, not of f, the white arrow above, but of the red arrow below. We are just, the red arrow below in our diagram, if you remember, that was psi composed with f composed with phi to the -1. This was a function from a piece over k to a piece over h, and we are taking the Jacobian matrix of this. So when we work in local coordinates, the push forward is just the multiplication of x times of the coordinates of x, which are a column vector, times the Jacobian matrix, which is usually denoted by with just this. I know it's confusing. I hope not too much. Now, the last couple of things, the differential of a scalar function. So we have a function from M to R. Its differential is a linear functional from the tangent space to R. So it's an element of a dual space. If you don't know what the dual space is, this is the definition. The dual space is the space of all functionals, linear functionals, from the vector space to R. Tm is the tangent space, its dual is called cotangent space. Its elements are called cotangent vectors. You can define the cotangent bundle, and a differential one form is a smooth section of the cotangent bundle. So it's a smooth map from M to T star M, such that every point, blah, 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 the same thing. So now, the differential of a scalar function is a special case of this. So df, when we write df, we are actually writing a differential one form. So something that takes, for each point, takes a vector, a tangent vector, and gives you back a number. So on the manifold, it takes a vector field and gives you back a function. So differential one forms are functionals on tangent vectors, tangent vector fields. So they eat a vector field and spit out a function. At each point, they eat a tangent vector and spit out a number, the value of the function at that point. You have the pullback. So if you have a function from M to N, tangent vectors go in the same way, differential forms go back. And it's defined by duality. So the pullback of a differential form is the differential form applied to the push forward of the vector field. This is done point by point, and if you collect all those at each point, you get a differential form on the origin space. So if you have a vector field on the origin, you can push it forward to a vector on the target. If you have a differential form on the target, you can pull it back to a differential form on the origin. Well, now this part is not really interesting. I won't be needing it, but if you have a differential one form, you can integrate it on curves. Like you can pull it back on the interval, the curve is defined, and you can calculate the integral. And for the differential wave function, it just gives you the usual thing. So the differential wave function integrated on a curve is the function at the end point minus the function at the starting point. But this is, I mean, I don't even know why it's here. So, this is a lot. More will be coming in the next hour. I'm stopping the recording.